Okay. Yes. Cheers. Okay. So I mean, like following on from the stuff was discussed yesterday about like differential kind of Monte Carlo gradient based variational inference. So one of the shining or leading example of like in the application space is the variational autoencoder class, and that model became quite popular. Still is. There are, of course, alternative models to do generative modeling. So I'll talk a bit about just a basic, like going through what VAEs and just a very like whirlwind tour of like the basics of normalizing flow. And I guess that will help Rob to kind of pick up and go into more details about this. All right. Sorry. Okay, so most of this talk is like based on these two papers. Both are review papers. So obviously, I've tried to kind of match notations as much as possible and use same sort of notation. But basically, if you don't find some references of what I'm talking about, basically everything is from these two papers. And I like these two papers because it kind of gives some historical context as well as global scheme of things. And although both these papers are targeted at mostly machine learning community, but these papers are kind of, I would say, much more universal. So I think statisticians would also feel good about reading these papers. Okay, so just to start with like, what are the typical applications? Why people went to like variational autoencoders or all these sort of generative models is basically like, of course, you want to build density models for like high dimensional spaces, and not just high dimensional, very complex spaces, natural images, for example. But then, of course, you want to do more. So for example, in this application, you see that you build a latent variable model for these sort of images. And then in the latent variable space, you can do interpolation. So you see that you can change the mood of the face, whether smiling, whether sad, and you can all tweak that because you have a generative model. You can sample from it. So the whole basic idea or the goal of like where these type of models came from is like designing generative model for complex data. One another example. So for example, generating I mean, like this is Stone Age stuff now, obviously, but still, I mean, like at that time it was like quite state of the art. And so, for example, like you want to fill in kind of sentences which sound all right. So couple of examples for that. So more generally, this is basically the problem, at least in machine learning, it's called unsupervised learning. Why? Because you have much more images than you have labels. So for example, like you just click images, you upload stuff on internet, billions of images, but like to label them like, okay, this is an image of I being happy, this is an image of my cat, and that cat is furry. So you need a lot of free time and like very charitable people to do that. So it's not possible. And it's not just images, it's like every other structured data, like voice, like speech, image, video. So you have lots of data, but you don't have labels. So the general classic machine learning paradigm of classification or regression, that's all right. But then there's more data where we need to do some sort of unsupervised learning, generative modeling. In a statistical parlance, we would say density modeling, right? And so one thing from yesterday's talk is that, I mean, like when now I'm talking about the parameters theta, so I'm no longer considering that as like a random variable. It's like something we care about point estimate. So the random variable here is like that X, which represents maybe an image or maybe like a time series of like speech or text or something like that. Okay. So one way to build conditional distribution, expressive.
And why is the label?
Yeah, why is it? Yeah, it's like whether it's cat, whether it's dog. If it's cat, yeah, basically. So like, yeah. One way to build like more expressive model is basically if we kind of parameterize conditional distribution using some sort of nonlinear function. Again, nothing new about that. That's what we do for GLMs, right? We use a link function. It's only the point is now I'm going to chain the link functions built. So I spend a lot of time on actually doing link function rather than actually probabilistic modeling. So that's basically moving from like what we have done before to like what's this generative modeling thing is. And throughout this talk, for me, it is a function nonlinear transformation of its input. I don't care about what function it is. It's like if you have here heard those terms like convolution, neural network, and all these things, I don't care. I mean, like for us, let's pretend that it's just a function. It's just like a new link function. That's it, right? And so we, in case of graphical models, we can also do these things. We have some variables which are parents and some variables which are child, and then we can do again this conditioning using some sort of nonlinear function. And the thing is that these nonlinear function, or I would say these neural link functions, if you want to say so, they are parameterized, right? So they have some sort of parameters. We don't consider them random variables, but just parameters of the link function. So one of the model that kind of started this variation autoencoder business was like something called a deep latent variable model. So I have a very high dimensional space of data, complex density. We don't know what's the density of like all natural images, right? But then we can think of modeling that as a joint distribution between some tractable, simple random variable or latent variable Z. And then we can think of the actual data distribution being such an integral, which we cannot do in practice. And we don't know the density. But we can obviously fit conditional distributions, right? So that's basically what is a deep latent variable model. So we start with a very simple distribution, maybe a factorized Gaussian or some sort of, you think of P of Z is like a prior on a simple base distribution. Then we sample from it, generate a simple like Gaussian distributed random variable. Then we pass it through some sort of complex neural network, deep neural network architecture. And the idea is we start with, let's say, noise, and somehow this nonlinear transformation or this composition of nonlinear transformation will kind of modify this noise and bring structure to it. And then obviously, once we do that, we can then use any sort of like sum of our exponential family distribution to model that final conditional distribution. So this is basically a deep latent variable model. So whenever you hear the term variational autoencoder, that is not a model. This is the model. So if the model is deep latent variable model, when we apply variational inference to do inference of that model, then the model plus variational inference, that combination is what's variational autoencoder. Of course, the term autoencoder means something. I'll come to that. But this is a very important point. Like everybody like talks about like VAE. My model is VAE. No, VAE is not a model. The model is this one. All right. So simple, like if I have some sort of like binary image, right? Some pixels are 1, some pixels are 0. So obviously, I would use this sort of simple latent variable model. And here, the term decoder comes into picture. And decoder means simply that you have compressed information, or you have very simple information, maybe a Gaussian variable, and you decode in much further or much more information out of it, so that at the end of that decoding process, you get like a distribution or like a random variable that resembles an image, right? Okay. So obviously, what we also want to know is the posterior, because if we have the posterior, so if we have the data, and the data is just like whatever complex structured object we have, we want to do the reverse thing. We want to find the posterior. And once we have posterior distribution of the latent variable, then we can do what is basically posterior predictive. So we can then sample from the posterior predictive to generate new complex data, and then we can tweak the posterior, the past image that I was showing. We can tweak the posterior to generate a sequence of image from a smiling face to a crying face. So all these things need a posterior distribution. And the way we would do it is using variational inference, right? And here again, the phi is a parameter, like a variational parameter, which is not a random variable, right? So that's the basics general variational inference setup. The only new thing is that we, other than phi, we also have another parameter theta for the actual forward model, which is also like a deterministic variable. And the goal is to kind of minimize the KL between them, or some of the new divergences that you have learned this morning, to figure out the best configuration of phi and theta, right? The best configuration in the sense that you would have the better marginal likelihood. The more if you can increase the marginal likelihood from your model, that means your model has become more expressive. It's becoming closer to what the actual natural data distribution is, right? And we do that using maximization of elbow. One important difference from yesterday or the day before is that now you see that your variational distribution is conditioned on data. That's a difference. So here what we are trying to do is that we have, let's say we have thousands of images. Then we want to take the information in all those images, and somehow we want to compress it down to the latent variables posterior. So the forward process, that is the actual DLVM model, it is decompressing information from a latent space to the actual observed space, and the variational posterior is doing the reverse. So there is a compression going on and there is a decompression going on. Okay, and the trouble that's a useful thing, because we are trying to condition our posterior explicitly by data, which obviously we haven't been doing in the last couple of sessions. But that's interesting thing. But the problem is, like, we can have like 1 million images. Then we need 1 million parameters, because like every new data point, your posterior will have some parameters, and so you have some way to deal with it. So again, going back to that encoder decoder thing, is that you have a prior distribution on the latent space, which is here like a Gaussian, like isotropic Gaussian space. Then you have a decoding path where you are using one deep neural network or any function you might want to get to a very complex data manifold. And the posterior path, which is encoding, is going from the data manifold back to that path. And if you learn the parameters of these two blocks, then you can obviously generate new data, you can morph data and do all this sort of stuff. Okay, how do we going to do that? Very simple. We are going to basically maximize the elbow. And maximizing the elbow means we need to do reparameterization trick, because we have non-linear functions going everywhere. So obviously we have to rely on pathwise estimator. Why not the score function estimator? I had talked about that. So obviously we have to go to the pathwise estimator. And remember now, or note that the elbow is now parameterized by both the model parameter as well as the posterior parameters, phi and theta, right? And then obviously, just for recap, if we know the exact gradient, then we can do gradient ascent. And because we cannot access the exact gradient because we have the intractable expectation, So obviously we will use the pathwise estimator and reparameterization trick. Again, reparameterization trick is nothing, it's just you use the law of unconscious statistician, and so basically you kind of take the expectation with respect to kind of a parameter free distribution, and then because now you can push the gradient inside the expectation. And we have covered why this is a useful, because we have much more stable variances in this case. So using the reparameterization trick, here a way we can write a posterior in an interesting way. So we take a neural network, input the image or the data or the speech or whatever, and take the output and divide the output layer of the neural network, or the output, whatever the number of outputs, divide them into like parameters of a Gaussian, and then you have like a nice way to simply reparameterize using the one-liner transform, right? And needless to say that this is done using a factorized Gaussian. There's no need to take factorized Gaussian. You can take like the actual full rank Gaussian. In that case, you will have the mu will be there, the vector, and then you'll have your Koleski factor. Right? And see, using this neural network, we kind of manage to kind of control the data density. So even if we have a lot of data, we are passing the data through that network, so we are able to compress it. So we don't need a million Gaussians, right? So that's how you are kind of compressing the information that's in so many data points, right? And so that process is also called amortization. So basically, whenever you hear this word amortization, it means your variational approximation is conditioned on your data based on some sort of function. It doesn't have to be a neural network, it can be any other function, but because here we are trying to model complex data, so we care about neural networks. All right. So again, it's pretty straightforward that the original form you cannot obviously differentiate, and now obviously because you have done reparameterizations, obviously you can do the reverse mode automatic differentiation easily. So you have two functions, one function going from the latent variable to the, like that f is actually the decoder f, and so you can pass the gradient easily through that path, not this path. So obviously that way you can easily get the gradients of both theta and phi. So that's z, and that f goes to your actual output space. And so when you take gradients with respect to both the variational approximate as well as your model, you have like one fully differentiable path, so you can use it. Okay, so you can write the LO now using the reparameterization tree, and interestingly, you note that this is something kind of you'll find a lot of papers and all that, is that you can now look at these two terms as like a reconstruction loss. That is the it's basically how good my model is fitting, and this is basically the penalization or regularization. Right? And of course, now we can have the unbiased estimate, Monte Carlo estimate of the gradient, so we can do optimization. Now, why autoencoder? Okay, so if you look at this thing, so I have some input data, I pass it through my, so that Fi is my posterior neural network, which is parameterizing my posterior conditional density. So I pass it through there, and I create some sort of artificial bottleneck. So the information compresses down to a smaller dimensional latent variable. And then again, I extract information, and ideally this X and X dash should match. So, and that match, how good they are matching is basically this reconstruction loss. And now autoencoders have been there for like long time. So what all of variational inference does or Bayesian inference does is basically it adds some sort of regularization. So basically going back to like stuff that we already know. So that's why the autoencoder thing is coming. So you see that it's taking the data and kind of encoding it and then again kind of reconstructing it back. So compression and decompression of information. And this is like the algorithm from the actual paper. So very simple. Obviously, if you have lots of data, you will do mini batching that we have discussed previously. That's rather than taking your likelihood over all data, you will just take a subsample and then simply apply SGD. But obviously, we never apply SGD. We'll apply some other sort of algorithms based on momentum or adaptive learning rates. But basically, that's it. That's the thing. So problem is when you go and like, I have 10 minutes, I want to learn what's VAE, you come up with this word's inference model. It's a bloody posterior, right? But all these terms makes your life difficult because then you have to spend another 10 minutes to figure out that what they're trying to say. Okay. So maybe sometime they will try to say like statistics in maybe some like Hebrew or something where like, what the hell are you trying to say? But this is the problem. So ideally there is nothing. It's just like, if you think of like in terms of GLMs, you want to do Bayesian inference on GLMs, and then you do variational inference on GLM where you use your link function again to parameterize the posterior. That's basically variational autoencoder. That's it. So you don't need actually the neural network. I mean, like one good exercise is to do exact this thing with like our classic GLM models, right? So that's a fun thing to do. But exactly that's all there it is too. But obviously, the big research in this field is, of course, one is like designing good architectures that matters. By architecture, I mean like what should be our ideal form of these functions, right? So that's the important point of research. And then there are other issues is like, how can I get better bound and all these things. And so but that's like a tangent in itself, and there's many works on different directions. Okay, so I started with the images, and like this is one, like I would say, hello world of variational autoencoder. So you want to model or you want to model images of like handwritten digits, right? And this data set is very famous. It's called the MNIST data set. I think all of you might know already. And what you want to do is find like a latent space, right? And in latent space, you might also see some sort of clustering. So I see a lot of papers these days, mainly in biology, where people are applying VAEs to do kind of like, people used to do all sorts of NPV stuff 7-8 years. Those labs are now using VAE to kind of do latent space clustering and all this sort of stuff. But yeah, that's basically the fun thing about that. You have these complex data sets, or not data set, but like complex data distribution, and then how can you compress it down and you have some sort of latent representation. So another word for this is representation learning. I don't like that word, so I'm not using it, but anyways. So how do you learn representation of this sort of complex data? Okay, so what I'm leaving out, one is that a lot of times we see in variational autoencoder, some of the images become blurry. So that's one point. Why I'm leaving out? Because they are like contradicting things. Some people will say something, some people, and the fact is we don't know. So there's a lot of people, they have their own opinions why that's happened. And the point is that this blurriness is the reason why people move to GANs, but now they have again moved from GANs as well. So GANs is not state of the art. Now diffusion models is the state of the art. So life goes on. And KL annealing is one very simple thing. Is I'll just quickly. It's if you go to this term, what happens is some people suggest that if you want to have better images, when you do your variational inference, like if you look at my quote from yesterday, if you just penalize this term somehow or more, like you multiply the KL term with a beta, and then like for first 500 iterations or maybe first 1,000 iterations, you just make the model behave like a maximum, or make the inference behave like a maximum likelihood. So the initial, so what happens is like you're traversing this very complex landscape, right, which is your loss function. So it is not just non-convex, but it has all sorts of irregularities, right? So what happens is initially you want to just go for the mode, right? Let's target the MLE, and then once your optimization picks up, your optimization picks up momentum and everything, then you kind of bring in the KL term. So that's basically KL annealing stuff. And obviously, again, I think obviously annealing, melting, integration, right? Thermodynamic, MCMC, all these ideas can be applied, right? I mean, like, there's no stopping from applying those ideas, right? You know, so all these annealing, melt, parallel tempering stuff, like you raise your likelihood to a temperature and all, applied. And people try that, but like there is no robust, I would say, understanding. Okay, this is a universal fact. No. But generally in lot of, I mean, like almost always these days, people use some factor with the KL. Yeah, so that's what is KL annealing in short. And obviously the other 2 points, hierarchical VAE clustering, these are very application specific. So, I mean, like here you have 2 variables, what I have shown, X and Z, you can have like a series of Z, and then, but that's very application specific. So, yeah. All right, some more applications that, I mean, this one I really like. So VAE does not need to be only on images. You can do VAE on all sorts of stuff, different data. So this is like VAE in the space of molecules, right? So you want to learn a generative model on molecules, and this has become quite popular. Not just VAE, but generally, have anybody heard about this term called geometric deep learning? That obviously. So there's like, I mean, like a lot of work that's going on in this field is like extending some of the deep learning ideas to more complex data, graphs, let's say, algorithms and all that. So I like this work is because like at the end of the day, they want to do some sort of optimization, but your actual data is discrete. So obviously it's extremely complex to do discrete optimization. So you use a VAE to kind of encode your data into a continuous space, run some sort of optimization in the continuous space, and this application become quite popular. I mean, they're quite famous. So these are the sort of stuff you can do with VAE. And this is something that I have been working on. So that's why like, I kind of like this application is that you can do VAE for like time series data. For example, this is like from a paper from 2020, which is on like kind of doing generative modeling for like high dimensional time series. And here the idea is your Z distribution comes from a diffusion process. So you take your data time series, encode it into a latent diffusion process. That's your posterior. And on the generation, you have your latent diffusion process, and then you generate data from it. I just mentioned it on. So this is generation, this is recognition. The main theme of all this work is how do you differentiate. So find any sort of complex data or any complex model, figure out how do you extend automatic differentiation to that. You have a new VAE plus, and the list goes on. But yeah, sometimes you have very nice things as well. And this is also based on some very early work on like variational inference on SDs and all that. But yeah, this gives like quite state-of-the-art result. All right. So now that's just the part one, like VAE. I will now talk a little bit about brief introduction to normalizing flow. Okay. So again, back to the deep latent variable model. So in the DLVM, what we are doing is like we're having a distribution on the
Before we move on, can we sort of go back to the variational encoders? Like, how would you?
Which one?
I feel like I don't really have a good grasp of exactly how they what they do.
Yeah.
Can you go over that a little bit? Like, can you give me the intuition again of what the variational encoder is?
Okay. So which part, like,
for example, forward. No, there was something else. There was another line.
no, that we have time. But I mean, like intuitively, how can I say it's like
Yeah, maybe that's like where there was the one liner. This one here.
okay. So the target is to find a posterior distribution of the latent variable given my data.
The latent variable is Z, right?
Latent variable is Z, right? I have a latent variable. Let's say I have a prior on it, Gaussian prior. Sample the latent variable, pass it through a neural network, and at the other end, I would get a complex data point. That's my generation process, right? That's my generative model. Now I want to figure out how do I get a good posterior variational approximation for that. Okay, so if we don't know anything about variational inference, where is the okay? So Z come from 0, 1. I generate Z, pass it through some nonlinearity. Other end, I get X, some image, right? Now obviously, if I want to, my target is to find, this is my likelihood, X given Z, and this is my unnormalized posterior, and I've used Z, so let's just write name, right? So that's my like true posterior. It's right. Obviously, this is intractable. So back to variational inference.
Okay.
So what we do in variational inference, we have a Q distribution of Z. Let's start with that. That's what we have been doing yesterday.
Yeah.
All right. Now here is the open question. How do you choose that Q? So that's the question. So what we are doing up till yesterday, on Monday afternoon, what we said is that if we these are conjugate, right? Then we just take Q of Z as like a Gaussian with some parameters, right? And then you apply the Kavi algorithm, work is done. Yesterday morning, what I said was, if that is not conjugate, then again we can do that. Take Gaussian with some parameters, but now we will do some sort of, rather than, because these are not conjugate anymore, because of this link function, now we'll kind of use Monte Carlo expectation. That's the thing. Now the problem is posterior distribution of an image when my data is image. So like, let's go back to that figure.
Okay.
This is how my posterior looks like. Now I can get there by like using a normal. Okay. This is, I mean, like these type of posterior distribution, even we don't have good MC to kind of, I mean, like very complicated to get there, right? And so what should be a good proposal or good posterior proposal? So one thing is what I did yesterday. I was saying that you take Q of Z, right? And then you kind of sample from it. Let's say some, hope they can see me. Let's say I sample from it. And obviously this is not that complex. This is just a Gaussian, but then pass it through some transformation to get with Z. For example, that can be, but even that won't get us there. So the idea here is, rather than using this simple transformation, why don't we plug a full neural network.
Okay.
Okay, so now if I write this as T of some parameter phi, xi, and that T of phi is basically some sort of complex neural. That neural network is different from that. That's the generative process, but that's only for the variational part, the approximation part. So we kind of, rather than having very simple transformation, let's say we take a very complex neural network with some parameters, and then we kind of go to the output space. Hopefully, if we can figure out the best combination of phi and theta using whatever, let's say somebody comes, some oracle tells us, here is the best phi, that will take your, basically your latent sample, Gaussian, to that thing, okay? Then obviously, we can optimize theta and phi together to find a good approximation. And that's step one. But generally that is never done. I've not even mentioned in the slide because even that doesn't work. And I mean, like, you can do that, but what variational autoencoder come up with idea is, rather than starting from this, right? Rather than starting from this, straight away start, because at the end of the day, my posterior, true posterior is always like that form. So straight away start like that. And then kind of, so you take your X, pass it through some sort of F phi, and other end, you will get something out of there, which is basically, we treat it as like parameter mu and sigma of a Gaussian, right? And then I say that my actual target latent variable is distributed with this mu and sigma. Or
Okay, so instead of starting from generating that, no, you start from the data.
you start from the data, pass it through some neural network. Output is the parameter of a Gaussian. So this is basically a Gaussian distribution, but whose parameters are conditioned by neural network.
Okay.
This one. So
Good.
right.
Now I get it.
No,
Thank you.
it's I'm fine. Yeah. Any other question, please? Cool. Okay. But hold on to that idea, Filippo. Hold on, we'll come back to that idea. People who are working on this, they never started with that idea. They straight away went to that idea. Okay, that idea was also quite good, but people never started with that. And that's what I'm coming to now. Okay. All right. So one way to kind of do, I said, like, we have this deep latent variable model, which is what you have Z from some distribution, prior thing, pass it through some complex nonlinearity. At the end, you come up with distribution, some conditional distribution you can calculate. So I gave one example of, like, you take like a kind of categorical distribution, but then you parameter is the probabilities using some neural network. But here is the other idea that I was talking about, is that alternative, and the whole goal is to model the distribution of X. In variational autoencoder, deep latent variable models, we were targeting the conditional distribution of the data given some latent variable. Now in normalizing flow, we are looking into something else. That is, we take a sample from a known distribution, pass it through some transformation, right? Some sort of invertible transformation. Then we know the change of variable formula, right? So now we can write the distribution of Px as in equation 8. So this is a different formulation. So our whole goal is to figure out a distribution of P of X. Earlier, we were trying to go via, conditioning or like parameterizing conditional distribution, where those conditional distribution are from exponential family. That was the pathway in variational inference. Take a Bernoulli distribution, parameterize the logits, and the logits are a function of neural network. That was what VAE was doing. Now we are saying something else. Now we are saying generate a sample from a Gaussian, pass it through your whatever nonlinear function, and then calculate the change of variable. So that way also you can write a distribution for that. Obviously, I mean, no, people started working on this because nobody would go and work on this except one person back in 80s that this is crazy idea. Why would somebody do that? Right. But again, all crazy ideas come to life with good engineering. So that's but anyway, so that's the thing. Is it clear, this thing, the difference between the model in equation 7 and 8? Both are trying to get a model of P of X, but in two different ways. All right. Okay. And obviously, as like
and the difference is that one is a neural network and the other one is transformation that and that you can calculate.
That transformation, for now, we are not talking about the transformation. Some transformation you can calculate, but the transformation should be quite good so that you can get from Z, which is a Gaussian, to X, which is God knows what, right? So you need to have a very good transformation. If you can, figure out exactly that transformation, and we have done. So for example, what is let's think of like a diffusion process, right? In a diffusion process, we know like initial value or the starting value. And then what do? We just kind of uncarry the Markov process. At the end, we find a stationary distribution, which is much complex. That's what we do in MCMC, right? We start with something we know, and then we kind of do a series of transformation, which is exactly the kind of MH kernels. And then at the end, we know that we'll get a nice distribution or the target distribution. Just think of what we do in MCMC. The only thing is we exactly know the properties of all those all those transformation, and basically we do not need to do this thing, right? The Jacobian adjustment, because that's the beauty of MCMC. But is think in that way, that like dynamical system way. All right. And so obviously we can compose those transformation, right? And obviously we can, it's just simple like chain rule. That means if we have some simple transformation, we can actually do a composition of transformation to get something more interesting out of that. Okay. So that brings us to what is called a normalizing flow. Okay. So the idea is you start from a base simple distribution, a Gaussian, which you know, and then you kind of flow that mass through those kind of transformations. So please think in terms of a dynamical system. We start with the initial value, we kind of flowing through a sequence of transformation. And we say that let's say we do 20 transformation, and we say what we get out of the 20th transformation, because those transformation when composed together would give us such a rich function that at the end we will get to a much more complex manifold. So my initial value of the dynamical system is coming from a Gaussian, but when I pass it through this discrete dynamical system, then I will at the end get what is into a much more complex state space. And that state space is what we want to model. That state space is basically the image or sequences or video, whatever. And it's called normalizing flow, since if you do it in the reverse direction, you have from a complex thing, so you kind of normalize back to your simple Gaussian. So that's the term that people say. I mean, like, yeah. For me, I think of it, I mean, like, obviously, I guess Rob will have a different interpretation or something. It's easy for me to think in terms of dynamical system. I have initial value, and then I start and then I flow through bijections, and then at the end I will have a complex density. And this is useful all because of automatic differentiation. And that's what my opinion is, because of course there is nothing complicated in the idea. The thing is that how would you do that? If you have to sit down and analytically do all the derivations, obviously you can do, but nobody would do. There are better things in life to do. So because we have reverse mode and forward mode automatic differentiation that I was talking about, this can be done easily, right? And so the original, and then the thing is that, which Philip was saying, that we can actually use this transformation, or we can learn those transformation from data, because we can write down the density, right? Use any standard maximum likelihood thing to kind of learn those transformations. And so that idea first was in this paper, as well as that paper. And then this guy or these guys, they kind of brought into machine learning, and then it has become quite popular. One thing that's why I mentioned, these guys are never cited in machine learning papers. So I pointed out in a conference that you should cite them, right? But they don't cite this, and they have done it in 2012. And again, if you think of this idea is like you have some base measure, and you want to kind of transport mass from this base measure to some other measure, right? That's that one, whatever the density is. And that's basically the classic problem of, measure transport, optimal transport. So people have done link with optimal transport theory and all that. But anyway, so the basic idea is very simple. Simple density, flow through compositions, you get another density, and you can calculate that density because you can differentiate those compositions. So that's basically the idea. Obviously, here comes neural network. So how you parameterize that T transformation, it depends upon various things that comes into picture. I'll leave that to Rob to go into like the crazy depth of how do you do that. But generally, I think these are the points that people like to, for example, you want to calculate the Jacobian determinant cheaply, right? That is something you want to do, because obviously you have to calculate a lot of determinants, right? And they are costly, right? So obviously you need, if you have lower triangular transformations, right, then those calculations are easy. And also remember that these functions, like you have to ensure that these neural networks are invertible, but that doesn't mean that explicitly they are. Sometimes you have to do some sort of root finding algorithm to do that. But these days people are like coming up with exactly invertible networks, which are easy to do and all that. But that's basically it. And the architecture is that comes from like all these considerations, what you want to do, what your target is. Do you want to sample from it? Do you want it for density modeling? So all these things, because at the end of the day, this is a way to express a very complex density. Now, there can be hundreds of things you can do when you, like from a density modeling point of view. So going back to what we started with variational inference, going back to there, Filippo, see, you have QZ from some simple normal distribution. Then you pass through those transformation. And at the end, you get a nice variational approximation. And you plug it back into the standard elbow formula, you get this out. So VAE was this thing, this path where you condition on the data, and this is the other path. Now you can be super you can be super crazy, and you can condition this initial factorized Gaussian with data as well. So you can do this way. Start with data, come up to here, don't sample. This is here. So you come up to here, do not sample. Here is your sample an intermediate variable, then pass it through your transformation, and then you have Z. And you can calculate all these things easily because you can differentiate through everything. And so that will be some other neural network. This I've written it F5, let's just write it F like eta.
Why would you do it in 2 steps?
You can, I'm just saying this is you can. So if you do it, first step is variation autoencoder, second step is normalizing flow. You can do it separately, call them different names, you can combine them together. So you can do, the basic idea is this. I mean, like at the bottom line, these are the 2 ideas. One is doing a transformation of the simple random variables and then calculating the Jacobian adjustment. Other is like take that simple random variable and pass it through some transformation, but the output of the transformation is not the target variable, it's just parameters of some exponential family distribution. So that 2 approach gives us 2 different things. And you can get quite nice, I mean, like these are like not at all state of the art. It's back from like almost 6-7 years back. So if you get more composition, so that's k equal to 2, k equal to 8, when you go to k equal to 32. So you have 32 transformations, then you can kind of, but I mean, like these are like now they have much better things, better models. You don't, I think you can have much better. Obviously, this is like 2-dimensional, but like obviously, yeah, even in that, like this is why people got so excited about this. I mean, like I know people who've spent their lifetime to design an MCMC sampler to target 4, right? And still it's difficult, or target 3. And so when you see that, all you need to do is just write down those 2 equations, throw in an automatic differentiation software, and that's it. So that got people really excited, and in not just in machine learning, everywhere, right? So people are using this for designing new MCMC algorithms. So yeah. Okay, I will talk about one example only. That's something, I mean, like I and Sam were discussing yesterday, and the creepy example. So here is one application. So think of like a simulator model, black box simulator. So for example, you can have like a very complicated dynamical system where you cannot evaluate Markov jump process, right? You cannot evaluate the transition density. So any sort of simulator model where you are kind of those why is some natural phenomena, can be a disease, epidemic, or something like that. And we have many such models, right? And the general go-to algorithm is ABC for this type of model. So last 4 years, I think normalizing flows has been used in this, because ABC, the problem with ABC is it takes millions of simulations. And if you have those complex models running ABC, it is very expensive. And we, I mean, like I work on epidemics. So in epidemic modeling, we are now thinking of building a model for 50 million people, one model that will track everyone together. And so it takes maybe 1 day to get one simulation, right? So ABC is too expensive. So maybe we need even better sample efficiency. So here is one way. So kind of using normalizing flow to directly do Bayesian inference. So the concept here is conditional normalizing flow. The same thing, you have a transformation, but now you are conditioning that transformation with using some other variable. Once you do that, you can then write down your conditional density using that same Jacobian determinant adjustment. Once you write that down, you can then learn the parameters of that transformation by simple maximum likelihood. And the data for maximum likelihood comes from the model simulations. Once you do that, then Bayesian inference is just, you just condition on it using some observed data. And that's it. That's this one shot Bayesian inference done. No MCMC, no variational inference, nothing. You need a model, put some inputs, record some outputs, pass it, then feed a conditional normalizing flow. You're done with Bayesian inference. So that idea has become, I mean, like it's growing like crazy now. Yeah. So these, I think, one of the very hot thing that's happening in ML. Obviously, you have to find a good neural network architecture, but I have played with this type of things a little bit, and generally they are quite robust. I mean, like I am nowhere. I consider myself even like a I am very rookie as a deep neural network or deep learning person, but even I can figure out or fit this type of models, and they are scary good. So this is how good they are generally sometimes. So this is a stochastic time series model. And how many of you know Simon Wood? Everybody, right? So Simon Wood wrote a paper on fitting these models, and it was published in Nature. And that paper kind of showcased the synthetic, like everybody knows what is synthetic likelihood thing. Yeah. So that was done using synthetic likelihood. And this is kind of, there's a new paper, I think 2020, they compared. And I like this example very much because you see this fourth variable, U. The model does not have that variable parameter. So what they did was they put a prior on a parameter that does not even exist. So if my algorithm, whatever my inference algorithm is correct, it will give me back the prior. So that parameter doesn't even exist. And it kind of does same. Obviously, this is millions of simulation. This is 100K. Okay. Up to now. I'm done. That's it.
Okay.
Yeah.
Questions?
Cool. 1 hour.
I guess we can take a short break then.
And I have, like in my GitHub repo, I have put like a variational autoencoder, very simple like example. So if anybody wants to run through it, they can find it. Yeah.
Easy. Yeah, 1 hour and a half. Yeah. And before.
Oh, so 1.5 hour.
Yeah.
Oh, okay.
1.5 hours.
Oh, okay.
And, yeah, I think I'll try to go through Sanmitra's code and yes.
By the way, this is the it. Anybody like no? This is the Git repo, and this is the IPython notebook. You can do the same. Is that you will find the open in Colab.
Yeah.
If you click, it will open. One thing I just want to say that it needs GPU. So once you go to Colab, click runtime, change runtime type, and here you should choose GPU and IRAM, and that's it. So it will run on GPU then.
Okay. Cool. Yeah, let me stop the recording.
Yeah, sure.
I'm just stop thinking.